Good morning, everybody. Today I'll be presenting your project on predicting the electrical output of the combined cycle power plant. For our project, we'll be using the supervised learning approach. Our target variable, which we aim to predict, is hourly electrical energy output, abbreviated as PE. To make these predictions, we'll be using four input variables: ambient temperature, ambient pressure, relative humidity, exhaust vacuum. To evaluate the performance of the model, we'll be using R square as the initial metric. R square is proportion, measures the proportion of variance in the target variable compared to the input variable. The high R square indicates a better fit for our model. After analyzing the initial dataset, considering the correlation between input variable and our target variable, we have decided to focus on the two main input variables, ambient temperature and exhaust vacuum. These variables have shown a stronger correlation with the net hourly electrical energy output PE compared to the other variables. We have chosen to include ambient pressure and relative humidity in our model due to high. We have not chosen because of the low correlation with the target variable. The R square of the ambient pressure is only 0.26 and the other one is only 0.158. Our model will be starting with a linear algorithm. Linear algorithms are well suited for problems where there is a clear linear relationship. To show you, we have PE versus AD mapped. There is a linear relationship mapped with the formula y equals to over here. The same goes with the PE versus V. So this will be our model sub-selection. To ensure the robustness of the model, we'll be splitting our dataset into three subsets: training, validation, and testing. We will split the entire dataset into two parts: 80% of the combined training and validation set, 20% for the testing. The initial split allows us to evaluate our model's performance on unseen data. Next, we'll further split the training and validation into two parts, 60 and 20%. The training set will be used to train our linear model, while the validation will be used to fine-tune our model's hyperparameters. I'll show you in a minute how this output has come. We conducted a feature selection experiment by training three different models by varying combinations. Model 1 only uses ambient temperature and achieved an MSE of 30 and R square of 89.89. Model 2 does the same, 25 and 0.9291. And the final model, which achieved the best performance, is when we include all of them, MSE of 21 and R square of 90.92, which is 92%. Based on this result, we conclude that using all four input variable provides the most accurate predictions for the electrical output of the combined cycle power plant. The inclusion of AP and RH, despite the relative uh, lower correlation with the target variable, contributes to the overall performance of the linear regression. So this is the feature that we selected. However, we didn't stop there. To further improve our performance, we compared the linear regression model with a random forest model. Let's call it model 4 and 5, using the best features selected earlier. The random forest model, with its ability to capture the non-linear relationship and, and handle complex interactions between variables, demonstrated superior performance model on the combined training and validation set. When evaluated on the training and the test set, the random forest model achieved a mean square error of 13.17, which outperforming the linear regression model. This finding helps us exploring different models and not settling for the first approach. And also we saw that our R square is not correct. By comparing the linear regression model with the random forest model, we were able to identify a more accurate and robust solution for the predicting the electrical output. Let me pull up the Python code that brought it up. So initially the data is split. The data is loaded from the CSV file and split into training, validation, and test using two-step process. First, the data is split into combined training and validate at 80 and 20%, and the remaining 80% is further split into 60 and 20%. And we have a part of code that compares the performance of the linear regression using feature combinations of we call it model 1, 2, 3 on the training set. The best feature combination is selected based on the lowest mean squared error and highest R squared value on the validation set. The best linear model is then compared. The best linear model with the best feature set is compared with the random forest model using the best feature combination identified in the previous step. The models are then trained on the entire training plus validation set and evaluated on the test set. The code outputs the best model and its corresponding best validation method. And here's the output of the code. We have seen this earlier in the earlier slides. That's all I have. Thank you for your time.